part one down of our final challenge and moving on to part two. So in part two, we are going to be running a hypothesis test for means. In our final challenge, I have included these formulas for test statistics because we will need them here. But before we kind of jump into part two, I do want to come back up and just note that I did go ahead and fill in the rest of these sample statistics. So in the previous video, I didn't find all of them for the sake of time, but I did now in between these videos. So I went down, or I'm scrolling down to show you my overall score now has increased to 30.5085%. So as a reminder, this is self-grading and you can see if you are correct as you enter things. So you will know exactly what you are earning on this before you even submit it. Okay, so for hypothesis test for means, it is generally thought that the mean number of words spoken by women is about 16,000 words per day. What we're going to be doing here is testing the claim. I'll scroll to the right. Testing the claim that the mean number of words spoken by women in between the ages of 18 to 29, which is our population, and that's what our sample is from, is less than 16,000 per day. We are going to use a significance level of 0.05. So we have learned that that is alpha. That's like our cutoff for what our p-value is too big or small enough to reject the null. So here, let's kind of think about what our null hypothesis is. If we look at this drop down, so you'll see any of the yellow cells have drop downs. The blue cells, you have to enter functions or numbers. So here we're dropping down. We are looking at means. Keep in mind the null hypothesis will always include equality. The alternative will not. So in this case, because it says that it's generally thought that the mean number of words spoken by women is about 16,000, we're going to put our null hypothesis as mu, which is the population average, is equal to 16,000. So this is kind of like what we're assuming to be true until we run this test and then figure out if we still believe that it's true or not. I'm going to scroll down to make sure that that was counted as correct, and it was, because that was 30 something before. So this is our null hypothesis. Our alternative hypothesis generally comes from the claim, as long as you remember that the alternative will never include an equality sign, like a less than or equals, stuff like that. It will always be strict. A strict greater than, strictly less than. So here, notice that it says test the claim that the mean number of words spoken by women is less than 16,000 per day. So what we're going to do here is use our drop down and go select mu is less than 16,000. And let's go check our score. Great. Okay. Degrees of freedom. Notice over here there is a note that says degrees of freedom is n-1. So when we're working with our hypothesis test for means, our n is coming from the number of women because that's where our population is. We're thinking about the population of women speaking however many words per day, and our sample is coming from women. So our degrees of freedom will be coming from the n, or the sample size, for women. So if we come over here, one way to figure this out, oh, and I did mean to say, at the very top here, it does say show all scratch work and calculation. So you don't have to show a bunch of extra work, but if you are doing extra work, and we will later, you'll see in these videos, please make sure you leave it over here so I can follow kind of how you were doing things. But scrolling down here, if I want to find n, if you remember, n is the number of data values. One way to do that is to highlight these, and it'll tell you at the bottom how many are there. But I'm going to go ahead and formally count this. So I will use the count function. I'm going to count how many are here. So click and highlight. Again, we're looking at the female sample because we are considering the female population. When I count, we have 31 data values. And so that is our n. So our degrees of freedom would then be 30. Now again, this is taking exact values. 30 is an exact value, so you could just type in 30 and that would work. I'm going to go ahead and start using referencing cells to, I'll say, get us used to that in these videos, because very soon we will be referencing a lot of cells. So because I calculated n over here, I can click on that cell and then say -1, because that is our n value, -1. When I hit enter, it should give me 30. And again, it shows a value rounded to 2 decimal places. And we can come down here, and that was correct. Way to go. Okay, our test statistic. This is going to take a moment. So our test statistic, I put this over here to remind us of what these are. Now, we are looking at a hypothesis test for means. And if you remember, with means, the type of distribution we use depends on what we know. So if we know the population standard deviation, or sigma, we can use the normal distribution along with the central limit theorem to run this hypothesis test. In this case, we do not have the population standard deviation. And in reality, it is so unlikely ever that you actually have the population standard deviation. Almost always it's sample in real life. So we will be using our test statistic of t. So we have a t distribution here. And in fact, I'll just go ahead and like highlight this. I don't know why I can't figure out how to highlight that right now. So I'm going to take our little drawy thing and circle it. Okay. So, oh, now I have to go click this. All right. So we're using our t distribution. So our test statistic will be a t-score here. So we need the sample mean. So x bar is the sample mean. We need mu, which is what we assume to be true, which is 16,000. And then we need to take S, which is our sample standard deviation, which if you remember, we found all the way up here. So that's our sample standard deviation. And we also need N, so the square root of N. So I'm going to do some scratch work for this off to the side because I don't want to necessarily type all of this. You totally can type all of this into this one cell, but I like to kind of break it apart a little bit. So this bottom part down here, the S divided by the square root of N, if you remember, that's called the standard error. Standard error. In other words, it is the standard deviation that we're using for our distribution after applying the central limit theorem. So to find the standard error, we can type equals, and then notice we're taking our sample standard deviation and dividing it by N. Okay, so we can come up here, grab our sample standard deviation. So again, you just click on that. Once you type equals, you should be able to click on this cell and it'll kind of do this little dancy border thing. Okay, scrolling back down, we have equals that, which was our standard deviation for our sample. And we want to divide that by the square root. So we can use the square root function of N. And remember, this is our N, so we can type that. So I'm going to kind of compare this again to what I'm finding the standard error, which is the denominator of our t-score when we're finding that. Just like this is the standard error for proportions, this is the standard error for means when we know the population standard deviation. This is the standard error for us here. So we took the sample standard deviation and we are dividing it by the square root of N, which we found to be 31. Okay, so that's the denominator of our test statistic, of our t-score. So I'm going to go ahead and start typing in here now, but if you want to go break it up even more, please do. So here I need to start by, actually I am going to break it up more, but you can do it however you want to. Okay, so that's the denominator. Our numerator here, I want to point out, we are finding the difference in x bar and mu. So we need to first take x bar. So I'm going to type equals, because you always need an equals if you're calculating or using a function. Equals x bar. So come back up. That's the sample mean for females. So that's what we just grabbed. Minus mu. And in this case, we are assuming mu, or the population standard deviation, is 16,000. So when I hit enter, that's our numerator, and then the standard error is our denominator, meaning we're calculating how many standard deviations away from 16,000 our sample mean is. So I'm going to say that again slowly. Our sample mean of close to 15,000. Our test statistic is calculating how many standard deviations or standard errors away from 16,000 our sample mean is. If that value is very far away from the sample mean, then it will tell us something about our conclusion. but we'll get there soon. Okay, so our test statistic here, we are now taking this, which was our numerator, that's the difference in our sample and population means, and dividing it by the standard error. So now, again, we've broken this down so that we're really just doing a numerator divided by a denominator. I want to really emphasize, though, when you do that, you have to click on these cells. You cannot just type in the values you see. Reminder that the self-grading portion of this absolutely will count it wrong if you are typing in these numbers or rounding them. So you have to use these exact values by clicking on the cells. Okay, so now I will scroll down and notice our score went up to 38.98. I'm going to show you really quickly that if I don't do that, so let's just say I typed in this. This looks exactly like what we had just calculated. It will even look exactly like we had just calculated. But if I come down here, it was not counted correctly. So again, you have to use those exact values, which in life is also very important to use exact values. Rounding really can affect your calculations in a lot of ways. Okay. All right, so that's our test statistic. I will pause this video now, and then on the next one, we will finish part 2.